Welcome to the Shape of Space Linear Algebra. This lesson is on determinants. Recall from theorem 25 that there exist multiple equivalent conditions for a square matrix to be invertible. I copied the conditions down here at the bottom just to refresh your memory. So the second condition was A being invertible, but the other four are equivalent to that. The rank of A is n, the rows are independent, the columns are independent, and the system AX equals B has only one solution, which depends on the inverse. So in this lesson, we're going to find, among other things, we're going to find another condition for when the inverse of a square matrix exists. The condition is related to something known as a determinant of a square matrix. You may have seen this in calculus where we just talked about 2 by 2 and sometimes 3 by 3 matrices, but there's a more general definition for a determinant, which we'll talk about here. We won't go into the motivation, but I'll give you a reference listed here, linear algebra exploration. So I'll give you the actual link to that in the information to this video. So there's a few ways of defining a determinant. This is the way we're going to use here. A determinant is a function defined on a square matrix that has the following properties. So the determinant of the identity matrix is 1. The exchange of two rows multiplies the determinant by a -1, so it changes the sign of the determinant. Multiplying a row by a number multiplies the determinant by that number. And adding a multiple of one row to another row does not change the determinant. So the determinant is just a real number. Should have said that up front here. It's just a real number. So the input is a matrix, a square matrix, and the output is a real number. And these conditions are written in terms of rows, but we could have switched in the word column, and it would have been an equivalent condition. In terms of notation, we write determinant A, which I'm pointing to here. We have the following theorem, which we're going to use eventually to evaluate determinants. A matrix with two identical rows has a determinant of 0. A matrix with a 0 row has a determinant of 0. A matrix is non-singular, in other words, invertible, if and only if its determinant is non-zero. So that was the other condition I mentioned about when a matrix is invertible. The determinant of a matrix in row echelon form is the product of the elements along the diagonal of the matrix. And I could have replaced row with column in statements 1, 2, and 4, and the theorem would still be true. But I'm just going to prove it in the case of rows. So let's look at the first statement here. When two rows are exchanged, the sign of the determinant changes. That's from the definition, but the matrix remains unchanged, right? If the two rows are the same, you don't see any difference in the matrix, and thus the determinant before and after the switch of the two rows must have the same value, and this can only happen if the value is 0, right? Because if you're changing sign and it's anything other than 0, it's going to be a different value. So that proves the first one. Okay, number 2, multiply the 0 row by any number A not equal to 0. By definition of a determinant, this changes the determinant by the multiple of A, but the row is unchanged, right? It's a 0 row, so if you multiply it by A, it's still all zeros. Thus, the value of the determinant remains unchanged, and this can only happen if the determinant is 0. Okay, so the first two are kind of easy. Number 3 and 4 are a bit harder, but I'll prove those on the next slide. Well, let's finish off the proof. I want to do property 4 on this slide, and then I'll use property 4 to prove property 3, which I'll do on the subsequent slide. So there's two cases, either A is singular or non-singular. And remember, singular means that it's not invertible, and non-singular means that A is invertible. Let's take the singular case first. So if the matrix A is singular, then it has at least one 0 row, as we're given that it's in row echelon form. So that follows from theorem 25. If A is singular, in other words, it doesn't have an inverse, then there's a dependency between the rows, and when you get the matrix in row echelon form, you're going to eliminate at least one of the rows because of the dependency and get a 0 row. By property 2 of this theorem, the determinant of A is 0, since it has a 0 row. Further, since A has a 0 row, at least one of the diagonal elements is 0. Clearly, when the 0 row crosses the diagonal, that element is 0. So in the case of a singular matrix in row echelon form, the matrix determinant equals the product of its diagonal elements. Then we have the other case where A is non-singular, in other words, it's invertible, and in row echelon form, then none of its diagonal entries is 0. That follows from theorem 25 again. Let's say the diagonal entries are AII not equal to 0, assuming A is n by n. So this is just the notation for the diagonal elements. Using item 3 from the definition of a determinant, we can divide out or factor out the diagonal entries and get A11, A22, all the way up to ANN multiplied together, times the determinant of some matrix called A prime that has the value 1 for each of its diagonal elements, since we factored this out. Using item 4 from the definition of a determinant, A prime can be reduced to the identity matrix, which has determinant 1 by definition. Now, the reason we can do this is if you have ones along the diagonal, you can use row operations to just use those ones to eliminate all the non-zero elements above them, and that doesn't change the value of the determinant. Thus, determinant A equals the product of the diagonal elements times the determinant of A prime, which is just 1, and then i.e. the determinant A equals the product of its diagonal elements. So there we have it. That's the proof of property number 4. Let's move on to the final property number 3, which I'll prove on the next slide. Okay, let's finish off the theorem, or the proof of the theorem. So property 3 is the equivalence between invertibility of a matrix and whether or not the determinant equals 0. If A is non-singular, in other words, invertible, then its determinant is not equal to 0. And if A is singular, we want to show that its determinant equals 0. So taking the first case, if A is non-singular, then we can put A into row echelon form with non-zero elements along the main diagonal by using properties 3 and 4 from the definition of a determinant. The determinant of the resulting matrix, which we'll call A prime, is non-zero by part 4 of this theorem. Thus, the determinant of A equals some constant times the determinant of A prime, which does not equal 0. In other words, the determinant of A does not equal 0. And the second case is if A is singular, in other words, it does not have a inverse, then it has a 0 row when put into row echelon form, which we'll call A prime. By property 2 of this theorem, the determinant of A prime equals 0, and by properties 2, 3, and 4 from the definition of a determinant, the determinant of A differs from the determinant of A prime by a scalar multiple, and thus the determinant of A also equals 0. Okay, so that completes the proof of the theorem. Maybe just one thing here that might be annoying you. This non-singular singular. Of course, it wasn't my idea to make up this terminology, but the idea is if A is non-singular, it kind of has a partner, which is its inverse, and if it's singular, it doesn't have a partner. In other words, it doesn't have an inverse. I guess maybe that's one way to remember it. I'm just working with the common definitions, so bear with me on that. Using the definition of determinant and some of the properties from the previous theorem gives us a way to compute the determinant of a matrix. And I have an example here, matrix A. We want to find its determinant. And I've put the steps down here, so let's go through it step by step. The first step is we can factor 2 out from the first row up here. That was one of the properties of in the definition of a determinant. So this equals this. And notice we're using these bars to represent a determinant. That's common, as opposed to when you have a matrix, you have sort of the little serifs on the top and bottom of the bars. So this is just common notation. Then going from here to here, I've taken the first row from the second and 5 times the first row from the third. And recall, for matrices, when you take a multiple of a row, including a negative multiple of a row, and add it to another, it doesn't change the determinant. So this equals this. And then we can take 8 times the second row and add it to the third, and we get this here. And then we can just read off the value of this determinant here, and it's just the product of the diagonals that came from our theorem, since we're now in row echelon form. So we get 2 times this product. 2 times 5 is 10. In the definition of determinant, we left open the possibility that multiple functions could fulfill the determinant requirements. The following theorem dispels that possibility. So for each n natural number, so in other words 1, 2, 3, 4, if there is an n by n determinant function, then it is unique. So assume there are 2 functions, f and g, that map from the set of m by n matrices to R, and that satisfy the conditions of the definition of determinant and the associated theorem that we just proved. Given an n by n matrix A, fix or determine some way of performing row reductions to get the matrix into row echelon form, keeping track of row scaling factors, in other words, factoring out a number from a row, and how the sign alternates on row swaps. Lastly, multiply the diagonal elements in the row echelon form of the matrix times any scaling factors, and that gives you the determinant. This process only uses the definition of determinant and the related theorem that we prove. Therefore, f and g must return the same value. Since f and g produce the same output on every input, they must be the same function. So this is more of just bookkeeping, I guess, to make clear that there's only one possible output given a particular input if we follow the definition of a determinant and the theorem that we proved. The Leibniz formula provides another definition of determinant that's equivalent to our previous definition. So given the same input, you get the same output as we had using our previous definition. The formula is sometimes useful in different proofs. We're not going to typically use this formula, but other than proofs. So it's 2 equivalent ways of looking at it. One is based on permutations over the columns, and the other one's over rows. And it's saying the determinant of A equals the sum over all permutations of n elements, so permutating from 1 to n, and it's the sign of the permutation, which is either 1 or -1. That's whether you have an even or odd permutation. I'll explain a little bit more about even and odd on the next slide. Times the product of the elements from our matrix A, where I is the first component and whatever the permutation is the second component. Or you could do it with the permutation over the rows. Okay, so that's quite a mouthful and it's a bit intimidating. The first thing to notice is this is the same as this. So there's just one formula here, but there's two different variants of it. And what it's saying is, first let's look at the permutations. This I, tau I, what is this? Well, let's just say we had a 6x6 matrix, then the I is across the top here. I is 1, 2, 3, 4, 5, up to 6. And then tau of I is what each of these numbers get mapped to. So 1 gets mapped to 3, 2 gets mapped to itself, 3 to 5, 4 to 1, 5 to 6, and so on. So for that particular permutation, you would multiply the entry A13 times the entry A22 times the entry A35 times the entry A41 times A56 times A64, and then you would determine whether this is an even or odd permutation. So you put a plus or minus sign there, and then you would go to the next one. All right, so there's quite a few permutations if you have a 6x6 matrix to work through. I'll show you a particular example, maybe an easier way of visualizing it for 3x3. So for 3x3, what we have an example here, and what we do is we take each permutation. So basically the permutation takes an element from each row and an element from each column with no overlap. So you don't have in each one of these products here. So the first one would be -1 times 7 times 4. So we go this way. Then the second one, and that's a positive permutation. Then the second one would be -1 times 5 times 2. So those are the only two if you pick this element here. And notice we had only one element from each row and each column. So that would be the first two sums in here. Then you would take 4 times 1 times 4. And that's an even, I believe. And then you would take 4 times 5 times 9. And that would be a negative permutation, an odd permutation. And then finally you would have -3 times 1 times 2, and then -3 times 7 times 9. So you would have a total of 6 different things in your sum here in order to get the permutation. And again, you'd have to determine whether each permutation is even or odd. If it's even, it's just plus. You don't change anything. If it's an odd permutation, then you need to multiply by a -1. Okay, so needless to say, this is more complicated than our previous methodology, where you basically are using row operations to simplify things. And the fact that these two formulas are equivalent here implies that the determinant of A transpose, where you take each row and make the corresponding column. So row 1 becomes column 1, row 2 becomes column 2, and so on. The determinant of A transpose equals the determinant of A, which we'll use that fact. Okay, so I'll give you a little bit more about the permutations being even or odd on the next slide. It's not a full discussion of permutations, although I have a reference where you can get more information on that. So let me give you a little bit more insight into whether a permutation is even or odd. I know this is a lot if you haven't seen it before, and I do have a reference here to inversion in Wikipedia, which is sort of the basis of making a determination of whether or not you have an an even or odd permutation. So let pi be a permutation. There's an inversion of pi, and I'm just using pi as the name of the permutation. Has nothing to do with the pi from trigonometry. There's an inversion between I and j. If I is less than j and pi of I is greater than pi of j. I took this example from Wikipedia. So we have one inversion here that's highlighted. So 2 is less than 4, so I is less than j, and then the permutation is pi of I, which is 5, is greater than pi of j. So that's one inversion. And then the Wikipedia article notes that we can denote the inversions by the pair of places, in other words, 2 and 4 in our example, or the pair of elements, 5 and 2. The inversions of this permutation using element-based notation are 3, 1, 3, 2, 5, 1. 5, 2 is the one we just looked at here, and then 5, 4. So we have 5 inversions, and the number of inversions is how you define whether your permutation is even or odd. We have an odd number here, and so that would imply in our formulas from the previous slide that this permutation would have a negative sign multiplied times it. There's another way of determining whether or not you have an even or odd permutation. You can write this as a cycle or a product of cycles, and the way you do that is you just start with 1, and you see that gets mapped to 3, and then 3 gets mapped to 1. So this is a cycle. It's a different notation. It's just saying 1 gets mapped to 3 and 3 gets mapped to 1. Then you go to 2, and you see 2 gets mapped to 5, 5 gets mapped to 4, and then 4 gets mapped to 2. So this is another cycle in our permutation here. So this notation is equivalent to this. But you can write this cycle here is 2, 5, 2, 4, and this product of two cycles of length 2, is equivalent to this. And there's only, how can I say it? A permutation can either be written as an even number of 2 cycles or an odd number of 2 cycles, not both ways. So it's written here as a odd number of cycles of length 2, and that's another way of determining that our permutation is an odd permutation. Sometimes using this cycle decomposition is an easier way of going about it. Okay, so sorry for all the additional material here. I kind of compromised between doing sort of a whole lesson on permutations and just giving you a short overview, since the course is really on linear algebra and not on permutations. So I hope you've seen this before. If you haven't, you may need to brush up a little bit more than the little bit I'm giving you here. There's a geometric interpretation of determinants. We'll look at the interpretation in 2 dimensions. For example, consider the vectors AC and BD in R2 and the parallelogram that they form, shown in the figure, this gray area. The area of the parallelogram is the determinant of the matrix formed by the 2 vectors. And I should say the absolute value of the determinant, because if it's negative, you don't have negative area. But other than that, it's the determinant. And so you just take A, C, and this is the first row, and BD is the second row. Take the determinant, take the absolute value if need be, and this is the area of this gray region. We have an example in 3 dimensions of an interpretation of the determinant. Take 3 vectors in R3, R1, R2, R3, and form the parallel pipet as shown here. Then the area of this parallel pipet is the absolute value of the determinant of R1, R2, and R3 is the rows in our determinant. And you can even extend this to Rn. You take n vectors in Rn. We're assuming these are linearly independent vectors. Otherwise, you're going to get something. You're going to get some collapse. And you define this set here. Basically, all the linear combinations of these vectors where the coefficient is between 0 and 1, and that'll give you an n-dimensional box. And the volume of this box is defined to be the absolute value of the determinant of the matrix whose rows are the vectors v1, v2, vn. So this is just a special case of this, and in fact, the example in the previous slide is a special case of this here. We have some additional properties of determinants. I'm going to just state them here. I'll give you a reference to a proof in a book by Cutler, and I believe this is online, and I'll put the reference in the information to the video. So given matrices, square matrices A and B, then we have these following properties. The first one we kind of already know, because we're told that if you factor out a constant from a row, it's just k times the determinant. So if you multiply k times a, remember that's times every row in A, and so of course you would get k to the n. So we kind of prove this first one from the definition. Assuming A is non-singular, the determinant of A inverse is 1 over determinant of A. That's quite useful. The determinant of a product is the determinant of each, the product of each determinant. And then I think I mentioned this already, the determinant of the A transpose is equal to the determinant of A. I have a topic here that doesn't really fit with determinants, but I didn't want to have a separate video on just this one topic. It's only one slide long. So I stuck it in here. The Cartesian product of n sets, they don't need to be vector spaces, is defined to be the set of all n tuples given by this expression here. So here's your n tuple, and then you can take any combination of these elements from these sets. So A1 has to come from A1, A2 has to come from A2, and so on. And we've seen this for Rn. For example, Rn, n-dimensional Euclidean space, is the Cartesian product of R copies of the real numbers. Another example would be the multilinear maps. A multilinear map is a function of several variables that is linear in each variable taken separately. So here we have our function, and these are the Cartesian product of n vector spaces, then it gets mapped to one vector space. So if we hold everything constant except for one of these vector spaces, then we have a linear transformation, which is what I've written out here. So if we hold everything constant except for the ith term, vi plus another vector can be broken into this sum, and you can also have the property of factoring out a scalar. Again, everything except for the ith term is held constant, and that's true for every I from 1 to n. So it's linear in each vector space, with the other ones being held constant. That's why it's called multilinear. If we view the rows of an n by n matrix as vectors in Rn, the determinant of A is a multilinear map. So we can think of V1 as the first row and V2 as the second row and so forth. And then W would just be R, since we map to the real numbers. The determinant maps to the real numbers. And I'll give you a reference to a proof of that. We'll return to this topic of bilinear and multilinear maps in a later video series on tensors. I haven't made that series yet, but it's in a book I've written, so I intend to do that. And just one note here, I kind of alluded to it at the beginning, but I'll mention it a second time. The Cartesian product is formed by just sets. They don't need to be vector spaces, but multilinear maps are further specialization of Cartesian products where we do have vector spaces. Okay, so that's the end of this lesson. The next lesson's on similar matrices, diagonalization of matrices, and something known as eigenvalues and eigenvectors. So there'll be quite a bit in the next lesson.